Hello, this is the question 4 from 2015. This is part C. The other parts are on the model answers on the Blackboard system and are descriptive rather than numeric. This one relates to lifetime data and Miner's rule, which is a way of trying to predict the lifetime of polymer systems under load, particularly pressurized pipe systems. So here we have lifetime data in seconds, so this is the amount of time it takes before the pipes rupture under different stresses and different temperatures. And it says that the data fit the standard equations for Miner's rule and that the constant B is equal to minus 1,000. And what we need to do in this part is to determine the other two constants. Now what we need to do with this is to make sure we know what Miner's rule is. So I've copied this from the formula sheet at the end of the exam up here. So what we have is the log of the time to failure in seconds is equal to A, some constant, plus B divided by T is in Kelvin, times log sigma. Now in this case sigma, the stress is actually in megapascals, and then T is in Kelvin as well. So what we have here is three constants that need to be found. With the data that we have there, we could actually find all three of those constants, and I went through the method of doing that in the lectures, but it is too convoluted to do in an exam, so we're only needing to find two of them because we've been given what the value of B is. So the way that we need to do this is to work out which bits we know. We know time to failure, we know B, we've been given that, we know T, we know sigma for each case, and we know T on that one. So it's A and C that we need to find. So the best way of doing this is to rearrange that equation to put everything that we know on one side. So log of time to failure minus B over T log sigma is equal to A plus C over T. And then by putting some of the values that we know into this side, we can then either find A and C by a graphical plotting method or by a simultaneous equation method. I'll go through both ways so that you've got the gist of both ways, but that will take a little bit longer. Okay, so if we do it for each of the conditions, the first one, one thing to say is we've got 15 different conditions here, so we've got 5 stresses and 3 temperatures. So we could do that for 15 different points and plot them all on one big graph. However, there's no need to do that because the value of B is the bit that varies with, is the bit that determines the stress variation, and we know that, so we don't need to plot at different stresses. We only need the different temperatures because in our A plus C over T is only temperature that's varying. So we could pick just one of the stresses, and I'm going to suggest that we just pick the 12 megapascal one nicely in the middle and just use the 3 different temperatures. If you were to actually plot all 15 on the graph, you'd find that the 5 different points at the same temperature would pretty much plot on top of each other. Okay, so if we do that then for the 12 megapascal one, let's take the 20 degrees C first. So 20 degrees C, 12 megapascal. What we have here, we have the log of the time to failure. The time to failure here is 2.4 times 10 to the 6. We then have minus B. Now B is actually minus 1,000, so that becomes plus 1,000 divided by the temperature in Kelvin, which is 293, times log of 12 equals A plus C over 293. And if we work out this lot here, that comes to be equal to 10.063. We then do the same for the 40 degree C, 12 megapascal. And what we have here is log of the time to failure from the data table above, which is 3.4 times 10 to the 5, plus 1,000 over, now the temperature is 313, times log of 12, again 12 megapascals, is equal to A plus C over 313. And that is equal to 8.979. And we then have the 60 degree one, 12 megapascals, and we have the log of time to failure, which is 6 times 10 to the 4 plus 1,000 over 333 now is the temperature, times log of 12 is equal to A plus C over 333, and that is equal to 8.019. So now what we can do is we can plot a graph. We can, let's just call this the value. So what we could then do is we could plot the value versus 1 over t. And what we would then get is we should get a straight line with the gradient equal to c and the intercept equal to a. Now you can do that, and in the exam you will be provided with, if you had a question like this, we would be provided with graph paper to do it. And I do have one I prepared earlier, so this is the graph that we would end up with there. And if we do that, we find that the gradient there is 4992. So the gradient there is the value c, and the a value is minus 6.98. So that's the values that we get graphically. So that's all fine, but obviously that requires plotting, and there may be a simpler way of doing it. The other way we could do it is as a simultaneous equation. So what we have instead of this is we can take two of the points. So if we take the 20 degree 12 megapascal point, what we have here is that we know that 10.063 is equal to a plus c over 293, and the 60 degree 12 megapascal point, we might as well take them as far apart as possible to get as best accuracy as possible. That's equal to 8.019 equals a plus c over 333. So those are the numbers that we just worked out beforehand. And if we then just subtract one from another there, what we end up with is the difference between these, 2.044. The a's subtract from each other, so then that's c into 1 over 293 minus 1 over 333. And just rearranging that, we end up with c is 4985. And what we can then do is put that back into one of the equations. So 10.063 is a plus 4985 over 293, which, working it out, comes to a is minus 6.95. So what we've got there is two different methods of working out a and c. C comes to be around about 5,000, a comes to be around about minus 7. Depending on how you do it, you will get slightly different answers. There's no actual right answer for this because it is with simulated real data with a little bit of noise in there, so there may be some variations depending on exactly which data points you choose, but around about 5,000 and minus 7 are the values that we want for this. So the important bit with this is to rearrange the equation with the bits that you know on one side, the bits that you don't know on the other side, work out how to either plot it or use simultaneous equations. Don't use all the data if you don't need to, only look at the data that you really need to use. And that should then give you the values for the missing two constants that we need in this case.